this is PrachiGupta, and we are moving ahead with our next collab. This is the Calculus for Deep Learning collab. It's a beginner friendly collab where it will teach you the essential calculus concepts that make the neural network learn. While linear algebra defines what computation happens, calculus tells us how to improve the model. So, what we will learn here, we will learn about derivatives, the rate of change, sensitivity, the that is um, chain rule that is the big propagation foundation, partial derivatives and gradients that we will use for multivariable optimization, gradients, how neural network learn, we will see gradient descent, and we will see the back propagation, the heart of the deep learning. So, why the calculus matters for the deep learning? Because we have a training loop, we have forward pass that computes the prediction. Then we compute the loss, like how wrong we are, and then we again back propagate using the calculus to find the gradient. So calculus is used here. So we back propagate the calculus to find the we use the calculus to find the gradient in the back propagation, and then we again update the weights, move in opposite direction of gradient, and we repeat until we make like zero loss. So here we are building a math to train pipeline uh, to train an XOR MLP multi-layer perceptron with back propagation and visualize it what it learned. So let's start. So first I'll do the setup. This cell imports the core stack numpy for math, matplotlib for visualization, and plot style, do the settings for plot consistent and readable across the notebook. Conceptually, it prepares the tooling so later calculus and optimization ideas can be visualized clearly. So, uh, before diving into the derivatives, let's understand the big picture. The learning problem. Neural network have millions of parameter. So how do we know which direction they have to adjust to make the predictions better? So the answer is derivative. Derivative tells us the direction. Should we increase the weight or decrease the weight, and the magnitude? How sensitive is the output weight? How much we have to move the weight, like that, how increase or decrease the weight, that magnitude also it tells us. So let's see it by a simple example, that how does changing a weight affects the output. So in this cell, we define a simple neuron function with x and w input, where we return um, x and w multiplication. So basically, to model the simplest neuron, a linear unit, we have defined this function, and then we sweep the weights with w value, and compute the outputs to show how the output changes with the weight. So we are doing this here. So basically, this cell uses the simplest possible neuron that we have defined here, where we get the output as w cross x, the multiplication. So it picks one input x and tries many different values with weight w. So we have picked one x and we try many different values with weight, and by plotting the output versus weight, it shows that if you change the weight, the output also changes. So if you we have x as constant, and if we change the weight, the output will also change. That's what we are trying to show by plotting it. And the core reason, and this is the core reason calculus matters, and we want to know which direction to change the weight to improve the predictions. So this is simple thing that we are trying to show here. If I run it, uh, if we increase w by any amount, the output also increases. You can see if we increase the weight here in this direction, the output is also increasing in this direction. So this is the rate of change we have seen here. When we do changes in the weight value, the output also changes and they all increase together. So this is what we have seen, how weight impacts the output. Now we will move ahead to the next cell. We will compute the derivatives numerically versus analytically. So this cell shows how to compute derivatives in two ways. One is analytical derivative, which has the mathematical formula, and other is the numerical derivative, which is approximation using a small change. So the numerical idea is basically, if I nudge x a little bit, how much does fx change? All, and the purpose is to build intuition that a derivative is sensitivity measure. So in deep learning, we don't change approximations during the training, we rely on the chain to do it. So I'll just run it, and you can see. So in the output you can see we have defined this numerical derivative here. We are calling the f function here, and this is the f function we have defined. It gives x to the power 2. So whatever we are passing, x plus h and x minus h, the difference, this is called the central difference, and this is how the numerical derivative is calculated. And for analytical derivative, we are just giving x, 2 to the power x. So suppose we have a test value is 3, and we are passing it to numerical derivative and analytical derivative, and we will just see how the results are differing, and we will just run this cell. So if you see, function is this: at x is equals to 3, fx is equals to 9, and the numerical derivative is 6, and the analytical derivative is also 6, and the difference between them is 0. So they match. There could be tiny errors from the numerical approximation, but they are almost same. So these are the two ways we can compute the derivatives. And once we have done the derivatives, we will visualize the activation functions and their derivatives. So this cell plots activation functions like sigmoid, tanh, and ReLU, and it also plots their derivatives, so in their slopes. So we'll see. Let me just run it. So we are visualizing, we are plotting sigmoid, we are plotting tanh, and then we are plotting ReLU, and then we are also plotting their derivatives. Let's see. So this is a simple sigmoid, tanh, and ReLU, and these are their derivatives. So the sigmoid derivative gives 0 for larger value of x and vanishing to the gradient problem. The ReLU is a derivative of 1 or 0. So as we already know, ReLU either gives 0 or 1, so it's giving the same. Before 0, on the x-axis, all the values are 0. Values for values greater than 0, it's 1. And this is why ReLU became the default activation model in the neural network, because it's either 0 or 1. So why this is matters? The derivative tells how strongly the gradient pass backwards. Sigmoid and tanh can saturate derivatives, become tiny and vanishing gradients. But the ReLU is either a passing gradient slope of 1 or a blocking it. That is slope of 0. So it's either 0 or 1, and that's why it's better than this two. So let's move. We have seen the activation functions and their derivatives. So now we have completed the section 1, and we have understood the derivative, measure the rate of change, numerical versus analytical computation, and why ReLU helps in vanishing gradients. So in vanishing gradients, you can see sigmoid and derivatives have this curves, because of which they have this vanishing gradients. But with ReLU, it's either 0 or 1, so it helps with them. Now next we will go to the chain rule, which is the backbone of the back propagation. So how exactly chain rule works? The chain rule tells us how to take derivatives of a composed function. Suppose if we have y is equals to f of g of x, then d of derivative of y will be dy by dx is equals to dy by dg and dg by dx. This is exactly how the back propagation works. the gradients flow back to through each layer. So input layer, if we will pass the input layer, it will go to layer 1, the derivative, then layer 2, then layer 3, and the loss. So the chain rule multiplies the gradient backwards. Let's see it in the code. So we have this cell teaches us the chain rule with a simple function like y is equals to 3x plus 2 square. It breaks it into two simple steps. One is the 3x plus 2 and y is equals to g square. Then it computes the derivatives. So that is break the big derivative into two smaller derivatives and then multiply. That's what we are doing. So define g of x is equals to, first we will define this and then we will define the second part, that is the y, g of square. So we have defined our derivatives. We have defined derivatives of g, that is dg dx, and then here we are defining the derivative of y, dg dy. So this is what we have defined here. So once we get this, we will define our main chain rule where we will do dy by dg and derivative of dg dx. So this is our main chain rule, and this is how we have broken down it into four simple steps. So let's do a test for value 2 and let's see how it actually propagates and works. Let me just run it. So we have got x is equals to 2. First we will calculate the gx, then we will calculate the g square, which will be y. Now using the chain rule, we will get dg of dx. If we will do the derivative of this, we will get the 3 as result. If we do the derivative of g square, we will get 2g, and we know g is 8.0, so we will multiply 8.0 by 2 and we will get dy by dg. And now we have to give dy by dx, which is equals to dy by dg into dg by dx. So it will give us 3 into 16.0, that is 48.0. So which is numerically 48.0, and if you will put 2 here, so 3 into 2 is 6 plus 2, 6 plus 3 into 2 is 6, and 6 plus 2 is 8, and 8 square. So this is what we do in the chain rule. Let's move forward. I'll just quickly run it again. We can see the output is same. Now we'll move to the next part. So now here we will see the deep learning example where we will do chain rule through mini network. We'll create a mini network. So this is a chain rule, but now in a neural network style pipeline. So how does this pipeline actually works? First we will multiply by the weights, and then we will apply the sigmoid, and then we will multiply by another weight, and then we will compute the loss. So we got one input, we multiplied by weight, and we got one output. This output we will apply sigmoid. After applying sigmoid, we got an output. To that output we will multiply another weight, and to that weight whatever we will get, we will compute the loss, and that will be our output. So this is a neural network style pipeline. Let's see how we will do it. So forward pass computes intermediate values like z1, which will be equals to w1 cross x, which will be z1, and then a1 will be the sigmoid of z1. So a1 is equals to the sigmoid of z1, and what the z2 will be a1 into w2. So that's what we are doing, and then l, then the prediction is equals to z2. So the z2 that we will get will be our prediction, and then we have to compute the loss. So loss is equals to prediction minus true value into 2. So this is how we will calculate the loss, and then we will return all these values. So this is our forward pass through mini network. Then we will do a backward pass to compute the gradients. So forward pass we have done. Now we have to calculate the gradient. For that we will do the backward pass. In backward pass, we'll see how loss changes with respect to W2, then with respect to W1. So how does W2 and W1 are affecting the rates, that the loss changes, that we will see. So we have defined here DLD, so it will be prediction minus 2, and then we will store it. So basically we are doing a backward propagation. What we did here, we are just going the backward propagation here. So first we, like last we computed loss, so first here we are computing loss, then we multiplied with a1, so we are here again multiplying by a1, and then we multiplied with w2, so we are doing a1 multiplied by w2, and once that is done, before w2 we did sigmoid, so we are again doing the sigmoid, and before sigmoid we multiplied by x, so this is basically the back propagation that we are doing. And I'll just run it to see the outputs. We are just printing the outputs here. We've called forward pass and backward pass and printing the outputs. So this is our network, this is our forward pass. In forward pass we got x is equals to 2, we calculated z, a1, z2, and then prediction, and loss became 0.1724. Now in backward propagation, what we got, dl by dw is 0. Minus 6 and 0 minus 0.02. So the gradient tells how to adjust the weights and w1 and w2 to reduce the loss. Now if you want to reduce the loss, we have to adjust the w and w2 according to this backward pass. So this is how we calculate the backward pass now. And now we have understood the chain rule compose functions, how gradient flows back through the layers and mathematical foundation of the back propagation, and how do we calculate that how much weight we need to adjust to decrease our loss. So this is how we calculate it. And next we are going to go through partial derivatives with multiple variables. So let's, so basically, in neural network, they have multiple millions of parameters, and we need the derivatives with respect to each one. So partial derivative, we use partial derivative. A partial derivative is a measure of how function changes with respect to one variable, treating other as constant. We can define it as df by dx, the derivative of f treating everything except x as constant. So, and the gradient is a vector of all the partial derivatives. So the key property here is the gradient points in the direction of steepest increase. So we'll just go through it and we'll see the code what we are doing. So far we have used one variable like x, but neural nets may have many weights. So this cell shows a function of two variable x and y. It computes df by dx and then df by dy, that is change in f when x changes and change in f when y changes. Then this maps it directly to the deep learning. Each weight is like one variable, we need partial derivative for every weight, and the full gradient is just a collection of all partial derivatives. So we'll create a gradient that will be collection of the all partial derivatives. So this is what we are doing here, we are creating the gradient with all the derivatives here. We'll just run it. So you can see we have this function fx is equals to this, we had this 2 points, we passed f this points, df by dx is calculated like this, df by dy is calculated like this, and the gradient if is like the list of these two derivatives. So the gradient point towards the steepest ascents, and to minimize go in the opposite direction, so we always have to go to the negative gradient. Now we will visualize gradient on a loss surface. So this cell defines a 2D loss function like a bowl L, where loss, this is the loss function. So it defines the 2D loss function in a bowl, like a bowl. So it creates a grid of W1 and W2 values and computes loss everywhere. So then it plots the counters and the surfaces to show uh, so it creates a grid of W1 and W2. This mesh grid it is creating and compute the loss everywhere. Then it plots the surface where loss is high and where the loss is low, that is minimum. It also shows the gradients. The gradient points uphill, increasing loss. So to reduce the loss, we move opposite of the gradient. This gives a geometric understanding of learning. Training is walking down the hill on a lost landscape. Let me play this. See, if you see the output, this is a bowl shaped lost surface. So the gradient descent follows a negative gradient downhill. The red arrow shows the direction we should focus to move to reduce the loss. So we should move in this direction to reduce the loss. Will So our third part is completed. We have seen partial derivatives, we have seen the gradient vectors, how to create it, and then we have seen the gradient direction, how to get it and how to visualize it, plot it, all these things we have seen here. Now gradient descent and how neural network learn. What is gradient descent exactly and how neural network learns? So gradient descent is an algorithm that makes neural network to learn. How? It it is it has these two fundamentals. Gradient is equals to compute gradient loss and weights, and then we adjust the weight. So basically we keep adjusting our weight until our loss becomes minimum. So w new is equals to w old minus eta and the gradient of the loss with respect to weights. So this is the formula to calculate the gradient. We'll move forward with the code. So this is gradient descent implementation. This is actual algorithm for walking down the hill. It does what it does. It computes the gradient at the current weights and then update the weights. How it updates the weights? It updates the weight by the same formula that we saw earlier. This formula w new is equals to w old minus neta. So this is how it calculates the weights, and once it calculates the weight, it stores each step in history, so we can plot a path. We can plot the path later, and this is the same update idea that we used when training a neural network, that we use when we train a neural network. So I'll just run this. So we have one loss function, true minimum, we have initial weights, we have learning rate 1. So in step 1 the weights were this and the loss was 10. Then we adjusted our weights and our loss decreases. Then we again adjusted the weight and the loss amount decreases. We kept doing it until our loss become minimum, and this converge approximately to 1 comma minus 0.5. So this much change we have done to minimum the loss. So this is how we keep changing our weights until the loss becomes minimum. And let's plot it now. Let's visualize the gradient descent path that we have done right now. Now what this code is doing is it uses the stored history from the gradient descent. It draws the loss contours again and then overlays the path. It shows where the weight started, shows how they moved step by step towards minimum. It may also plot loss versus step. It helps us to see if loss decreases smoothly or oscillates. The main purpose of it is it confirms visually that gradient descent is actually minimizing the loss. So this is what it's plotting, and I'll just run it to see. If you will see, it's gradient descent roll down hills on the lost surface, and each steps move in the direction of the steepest descent. So this is how we can visualize it. And this is the learning rate effects. This cell repeats the gradient descent for different learning rates. It usually loops like for LR in small, medium, and large, and then it compares the behavior of uh, a small learning rate and then good learning rate and too large learning rate. That is very slow progress, steady downhill movement, overshoot and may become bounce and diverge. So this is the exact same tuning issue that um we can face during training a real network. So let me just run it. So first is when we very slow converge, when we did a very slow converge. When we did a smooth and efficient converge, that is the too right, just right. And if we do the too large, the oscillation may diverge. This shows the graph, the path. Now we have completed the section 4, that is gradient descent algorithm and how weights are updated and minimized, and the uh, crucial role of the learning rate. Now next is the back propagation, that is efficient for gradient computation. Now back propagation is the heart of the deep learning. Back propagation is just the chain rule applied efficiently to compute all the gradients in a neural network. Uh, Instead of computing the gradients from scratch for each weight, we do a forward pass, compute and save all the intermediate values. Then we do a backward pass, use the chain rule from the output to input, reusing the saved values. This reduces the computation from O of n square to O of n for n weights. So let's see how we will do it. So this is a complete backpropagation example of XOR problem, uh, where we will give two inputs, two hidden sigmoids and one output sigmoid. That is what we are planning to do here. So this is the main deep learning piece, training a neural network to solve an XOR. XOR can't be solved with a single linear layer. We need a hidden layer. So this cell defines a small neural network like two inputs, hidden layers, and then one output. So in this, first comes the forward pass that computes the hidden activations, compute the predictions, and compute the losses. Once the forward pass is done, then this is the forward pass in which it computes the hidden activations, it computes the predictions, and then it computes the loss. So that is what we are doing here in the forward pass. Once the forward pass is done, we will define the backward pass. In the backward pass, we are computing the gradients of the output layer weights. Here we are computing the gradients of the output layer, and then we propagate the error back to the hidden layer, and here we are propagating the errors back to the hidden layer. And once we do that, we compute the gradient for the first layer weight. So that is what we are doing here. So and then we are training the loop. Basically we have a training loop. We will again call, so we will do a backward pass and then we will return the loss. So this is a single neural flow that will happen. We have already defined the two sigmoid functions. So we will do a forward pass, we will calculate this sigmoid functions, activation functions, we will calculate the weights, the prediction, and then we will compute the loss. And in the backward propagation, we will compute the gradients of the output layer weights, then we will propagate the error back to the hidden layer, and then we will compute the gradients for the first layer weights, and then we will return the loss. So once that is done, uh, this is a single flow. Now what happens is here we have defined one x numpy array, one y numpy array, and we have defined a simple neural network, and we have defined a losses list. Now what we will do, we will call 5000 times we are doing epoch, and we are calling this gradient function. We will call this function forward, and then we will again call the backward pass, and then we will append the loss, and we will do it for every time for all the epochs. So this is a training loop. It repeats forwards plus backwards for many epochs, and then update the weights with each epoch. Once we update the weight with, here we are updating the weights, so with each epoch these weights are getting updated, and once we update the weights we store the loss so that we can plot them later. So in these losses we are appending the loss, and this is basically a manual back propagation training that we are doing here. So I'll just run this. So see, there are 5 epochs that happen, and you can see the loss rate is decreasing with every epoch. So this is the final prediction that we got. So if you see, now we will go ahead. You can see, like, if input is 0 0, the target is 0. If input is 0 1, it gets 1. If it's 1 0, it will give 1, and if it's 1 1, it will give 0. So this is the prediction it's doing. So now we will we will visualize the training. Whatever training we have done, we will try to visualize it using the results from the training, that is the losses and the trained neural network. We will first plot loss versus epochs, that shows the training actually converged. Then second plot we will plot is the decision boundary, and the third, let me just show you first. So this is our loss curve. Then we will print the decision boundary. We will plot them. Let me just run it. Yeah, so this is our training loss curve over the time. With each epoch increasing, the loss value is getting decreasing. So this shows the relation between them, and this is the decision boundary of XOR, that is 0 0, it will give 0. If it's 0 1, it will give 1. If it's 1 1, it will give 0, and then if it's 1 0, it gives this. So this is how it actually makes the basically it makes the grid of points in 2D space, and then colors the region based on the prediction classes. And this is that confirms that the neural network learned a non-linear separation, which is why the hidden layer matters. So this is what we have seen here, and now our section 5 is completed. We have seen how break propagation is used, how forward passes saves the value, and backward passes compute the gradients, and then how complete neural network learns. So everything we have here summarized, and that's all. Thank you for this. Thank you for your time. Thank you so much.